Welcome. In this video we continue section 3.3, the rules of differentiation, and we spend time practicing the rules. We will see that we can really apply these rules in a variety of situations. First we'll talk a little bit about some new notation for repeated derivatives. I will recall the basic rules, and then we will see some problems. Let's go. Notation. Suppose that f of x equals 2x to the fifth. Then f prime of x equals 10x to the 4. This f prime of x, that's called the first derivative. Now, I can take the derivative of the derivative, and that's f double prime of x, and that is the second derivative. I can take a derivative of that, get the third derivative, and the fourth derivative. At this point, it's a little bit ridiculous to keep writing primes, so the typical notation is to put the number of the derivative in parentheses up above, like an exponent. So the fourth derivative of this function is 240x, the fifth derivative is just 240, and the sixth derivative is 0. And in fact, from this point on, the seventh derivative, eighth derivative, and so on, all of those further derivatives will be equal to 0. There's a corresponding notation using the d over dx notation. I have my first derivative, that is the d over dx of 2x to the fifth. The second derivative, we read this d2 dx2, and then d3 dx3, the third derivative, fourth derivative, fifth derivative, sixth derivative, and so on. What if I want to evaluate a derivative at a point? With the f prime notation, that's pretty easy. I can figure out my first derivative, f prime of x, is 10x to the 4, and that's already in functional notation. So if I want to evaluate that function at 2, it is f prime of 2, and I substitute 2 for x. But what if I'm using the d over dx notation? Here, the derivative of 2x to the fifth is 10x to the 4, and now what happens if I want to evaluate that at 2? Well, we use this vertical bar subscript x equals 2, and that means evaluate the expression at x equals 2. The vertical bar isn't just for derivatives. Even in general, if I have any kind of expression and I want to evaluate a variable in that expression at some point, I can do a vertical bar and a subscript, and so the expression x plus 9 evaluated at x equals 1 happens to be 10. The line above it, I would say the first derivative of 2x to the fifth evaluated at x equals 2 is 160. Alright, recall the basic rules. We have the constant rule, the power rule, the constant multiple rule, the sum rule, and the derivative of e to the x. If you don't feel so comfortable with these right now, pause the video, take a look at those examples on the right, and make sure you have a good general understanding for how these basic rules work. And now, here's the most important part of this lesson. Let's try some of the problems. So to begin, here are two problems. Number 1, let f of x equal 2x to the fifth minus 3x plus 100. Compute the first, second, and third derivatives of that expression. Also, problem number 2, compute the derivative of that crazy expression there. So pause the video, give these things a good try, and then start again when you're ready to check the answer. Go to it. Okay, welcome back. Let's take a look. So for the first problem, there is the first derivative, the second derivative, and the third derivative. Check your work. The second problem is trickier, to be sure. The first step is not to take a derivative. The first step is write some of those x's in terms of powers. So this 8 times the square root of x, let's write this as 8 times x to the 1/2. And instead of 4 over x to the 8, maybe write that as 4 times x raised to the negative 8. That way, I know how to use the power rule to take derivatives. Now here is the derivative. Now I've actually taken the derivative of that function. So check your work, and you can see, for example, in those two boxed expressions, the derivative of 8x to the 1/2 is 4x to the negative 1/2, and the derivative of 4x to the negative 8 is, well, let's see, I had a negative 4x to the negative 8, so a negative times a negative gives me positive, and I end up with positive 32x to the negative 9. And then the last step, purely optional, is to take those x's raised to negative powers and re-express them in a more familiar notation. So I can take that first boxed expression and call it 4 over the square root of x, or that second one and call it 32 over x to the 9. All right, check your work, see how you did. The next set of problems, you'll have to do some kind of simplification first. You can't just charge in and take derivatives. So think about how you might simplify, expand, do something to these functions before you take the derivative. Okay, give it a try. Okay, and we are back. Let's take a look at some solutions. For the first problem, well, for number 3, you'll need to expand that. You get a big polynomial, and then just using the power rule and the constant multiple rule and the constant rule, we can simplify that to get f prime. For problem 4, distribute the square root of t. And when you distribute the square root of t, you get t plus 10 root t. And now the derivative is going to be 1 plus 10 times, and there's my derivative of the square root of t. In this example, I didn't go through the intermediate step of writing t to a power, that would be like t to the 1/2. Instead, I know that the derivative of square root of t is 1 over twice the square root of t. That's something that we've seen a couple times already. So if you need to take the derivative of the square root of t, just write 1 over twice the square root of t. You don't have to go through that intermediate step. For number 5, I can split up this fraction as x to the 5th over x plus 3x over x plus 7 over x, and that simplifies. Don't just take the derivative of the top and the derivative of the bottom. That's not a rule that we have. There is no rule that tells us to take the derivative of the top and the derivative of the bottom. I have to split this up into different parts, but then it is in a form that I can differentiate. So derivative of x to the 4 is 4x cubed. The derivative of 3 is 0, so that doesn't appear on the right. And then the derivative of 7 over x becomes negative 7 over x squared. And lastly, I do the same kind of procedure with problem number 6. And being very careful with the exponents, we end up with t to the 7/2 plus t to the negative 1/2. And that is something that I can differentiate using the power rule. Okay, moving on. Our last page of problems. Can you differentiate these using only the basic rules? In the future, we're going to learn different rules for differentiating all of these problems. But just think about the tools that you have at your disposal right now, only those basic tools that we've looked at so far. Which of these can you differentiate using those rules, and which ones can't you? Some you can, and some you can't. So see what you can do. Start the video again when you are ready to check your work. And we're back. Let's take a look. The first one, yes, you can differentiate that. But first, you have to split it up as the square root of 5 times the square root of x. Then it's a constant times the square root of x. So its derivative looks like that constant times 1 over twice the square root of x. Number 8, no. There are no rules that we have at our disposal at this point that help us differentiate that expression. How about number 9? No. Once again, none of our rules tell us how to differentiate that. We might be tricked into thinking that the derivative is, let's say, the power rule would say, subtract 1 from the exponent and then multiply in front. That no, this is bad. Our rule does work for x cubed. If my variable is in the bottom, then I know how to differentiate that guy. The answer for that one becomes 3x squared. But the rule doesn't work if x is in the exponent. Number 10, no, this is a quotient of 2 expressions, and our rules don't tell us how to differentiate a quotient of 2 expressions. But look what happens if that denominator is split up in problem number 11. Yes, this is something that we can differentiate. I can rewrite each of these terms as x to a power and then differentiate. Alright, so that is our quick reviews behind some of the power of the basic rules. Even though these rules are pretty basic, they are the foundational rules, we can apply them in a lot of interesting situations. And that's a good place to stop.